So tonight Doug Smith will be starting off with a presentation on the constellation Musa, which is in the southern hemisphere, and we will be following that up with the main topic, which I will be giving on some of the large structures that can be found within the Milky Way galaxy. Some of them found very recently, and by recently I mean within the last 3 years, and that are you wouldn't really have necessarily have thought of unless you're one of those people that pays really good attention to science news. So with that, Doug, I will let you start. You should be a co-host and have the ability to present.
Let's see if that works. Okay. Can everybody see the screen? Can I put up?
Yes.
All right. So the constellation that I am doing tonight is, I think it's pronounced Musca. So Musca is literally the fly. It's a fairly small constellation, very far down in the southern sky. If you look at the chart, you can see it's way down there. It's directly south of Crux. So it's about as far south as you can go almost. It's between -65 and -75 degrees in declination, and roughly between 11 hours and 14 hours in the right ascension area. So you cannot see it from Tucson. You would have to be a little farther south, I think. So Musca is one of the 12 constellations that was created by someone named Petrus Plancius from observations of somebody named Peter Dirkzoe Kaiser and Frederick D. Hoopman. I believe those were Dutch explorers who went down to the southern hemisphere, I believe Cape Town, in the 1500s, and this constellation was first published in 1597 in Amsterdam. The chart that you see down in the corner there is from the original Uranometria chart by Johann Bayer in 1603. Musca is that little grouping right up in here. It was actually called Apis at first. And you notice there's a constellation here called Chameleon. The chameleon is eating the fly. His tongue is sticking out and he's about to grab the fly, and that's exactly what it was. So Musca does not have any Greek history behind it or anything like that because it's a very recent constellation. If you took a picture of the Milky Way with Crux in the middle of it, there's Musca directly below Crux. It's got part of the Milky Way in it and has some clusters and things in it, which we'll go over, but that's what it looks like. The stars are not terribly bright in Musca. I don't think there's anything larger than third magnitude in terms of brightness, but it's easy to find because Crux is pointing straight at it. In terms of size, it's pretty small. It ranks 77 out of the 88 constellations. It has 10 stars with Bayer designations like Alpha Musca, Beta Musca, etc. None of the stars have names. And like I said before, being in the Milky Way like that, it does have clusters and some nebulae in it. Pardon me for one moment. background noise from my wife watching television. So I'll quickly go through the brighter stars. You can look at the chart here and you can see there's an alpha and a beta, delta, gamma, etc. So I'll go through them fairly quick here. So Alpha Musca is magnitude 2.7. So that's the brightest star in the constellation. It's 315 light years away. It's a B2. So it's a blue-white giant. It's got 9 solar masses. It's roughly 5 times the size of the sun. It's very hot. It has a surface temperature of 21,400 degrees Kelvin. It's blue-white. And it puts out about 4 times as much energy as the sun does. And it's estimated to be only 18 million years old. So it's a very young star. Beta Musca is a binary star. The total magnitude is 3.07. It's 340 light years away. Both of the components are main sequence stars. They're separated by 1.2 arc seconds, so you could look at them with a telescope and separate the pair. The A star is magnitude 3.5, and it's a B2, about 7 solar masses. The B star is magnitude 4, so that would actually make a nice pair to look at if you ever get down in the southern hemisphere. And it's a spectral class B3, about 6.5 solar masses. Delta Musca is a spectroscopic binary of magnitude 3.6. It's very close to the sun, 91 light years. It's a spectral class K23, which means it's an orange giant star off of the main sequence. And it's very cool, a lot cooler than the sun. What is that Greek letter? Alpha, beta.
It's phi.
Is that what?
I think it's phi.
Phi Musca? Okay.
Lambda.
Oh, yeah, lambda.
Lambda. Thank you. You're right. Lambda. Okay. Well, it's magnitude 3.7. It also is fairly close, 128 light years. And it's an A7, so it's blue-white. Gamma Musca is magnitude 3.9, 325 light years. It's a spectral class B5. It's spinning very, very fast on its axis, 205 kilometers per second. So it's very oblate. The polar radius is actually 7% smaller than its equatorial radius. And it is also a Cepheid variable with a period of 2.7 days. Epsilon Musca is magnitude 4. It's 300 light years. It's M5, red giant, about 130 times the size of the sun. And the luminosity ranges anywhere from 1,800 to 2,300 times that of the sun. It's a semi-regular variable with about 1.7 solar mass. Mu Musca, is that mu? Yeah. Magnitude 4.7. It's 450 light years. It's a spectral class K43, so it's a red giant off the main sequence. It's got 53 times the radius of the sun, about 600 times the solar luminosity, and it's really cold in terms of stars. It's only 3930 degrees Kelvin. And then what is that one? Eta?
It is,
That is Eta.
Eta.
yeah.
Okay, so it's magnitude 4.8. It's 400 light years. It's a multiple star system, spectroscopic binary with a period of 2.4 days, spectral class B8. And then the last one I did was Theta Musca, which is a very interesting star. It's a multiple star system, magnitude 5.5. The distance is 7,400 light years. It's a spectral class WC5. it's a Wolfrae Star, which is a very special star. It is the second brightest Wolfrae Star in the sky, and it's actually part of a triple system. The other components are an O6 main sequence and an O9 blue supergiant. The combined luminosity is over 1 million times that of the sun, but it should be pointed out that most of that is in the infrared from the Wolfrae. So it doesn't look that bright when you look at it in a telescope. Right, okay, so those are the stars.
That's super crazy to have two class stars in the same grouping
Oh,
like that.
yeah.
So that's
yeah,
pretty dang massive amounts of star
it
in that
is.
cluster.
Oh, yeah, that's quite a system. That one, let's go back to the chart. Oops. So theta is this one up here, right there. Okay, so we have some deep sky objects. In the chart, you see 3 of them marked there. There's 5189, 4833, and 4372. So 5189 is a very nice planetary nebula. It would be visible in an amateur telescope. It's magnitude 8.2, and it's approximately 3,000 light years distance. It's often called the S Nebula because it's got an S shape to it. It's very interesting, and that's located not too far from our Wolfrae Star, right there. By the way, if you don't know, these 2 big bright stars here, that's Alpha and Beta Centaurus.
Yeah.
Then we've got NGC 483, which is a really nice globular cluster, very rich, magnitude 9.8. It's 21,200 light years from the Earth. It's very old, about 12.5 billion years old. Like I said, it's a very rich cluster, as you can see in the picture. And then there's another globular cluster, 4372. It's magnitude 9.8, and it's almost 19,000 light years from the Earth. It also is around 12.5 billion years old. And it's not as spectacular as the other one. It's much smaller and much less interesting. It's very dense, though. It's very highly condensed. And I should have had this chart. So here are the 2 globular clusters there and there. And then there's some other stuff in here besides globular clusters. There's something called, and this is the official name. It doesn't have a number. It's not in an index catalog or anything. It's just called Darkodad Nebula. That's the official name. It's a dark nebula in the Milky Way, and it's a dense gas and dust, and it's actually one of the closest star formation regions to our solar system. And it was described in Sky and Telescope magazine as one of the finest dark nebula, one that is wonderful winding and very definite. And this is one of the globular clusters right here. And I'm not sure, but I think that's the other one, the 2 globular clusters that we looked at. And let me go back. You can see it in the picture. There it is, right there in the constellation. I didn't say anything about the Sac Nebula, which is this region right up here. The Sac Nebula does come down into Musca a little bit, but I didn't think I want to cover that because I covered that when I did Crux. So, any questions?
What's a Wolfrae Star?
I knew someone was going to ask me that. I looked it up the other day, but now I forgot. Connor, do you remember what that is?
Not off the top of my head. I
Okay.
can't remember if they're part of like a forming star or a star that's like there's like some infalling mass and
Give
it's
me a
shooting
second,
out
and I will.
polar jets. I can't remember if that's the Wolfrae Star or if I'm confusing that with hybrid Hero objects.
Give me a second, and I will find out for you.
So I always get those two mixed up between a Wolf Riot and a hybrid Hero object. They're very different. Like I think Wolf Riots are like progenitor pulsars or something like that. Like they're. Ugh.
Give me 1 second, Kay. I'll answer your question.
Yeah, I looked it up in the star atlas and it wasn't in here. In the index.
Okay, so now I remember. So Wolfrae Star is a star that's near the end of its life. It's burned off all its hydrogen. It has no hydrogen in its surface atmosphere, and you're seeing a lot of ionized helium and spectral lines of heavy elements. And it's in the very final processes. It's burning helium and other heavy elements being fused in the core, and it's blown off all its outer layers of hydrogen so that the spectrum has no hydrogen lines in it and has just very wide helium lines and other lines like that.
You can think of it as a precursor to a supernova, typically. Because you're only going to get a star that's going to do that if it is a supernova class.
Yeah, it doesn't say that in this article, but it does say these are very massive stars.
Yeah, so they're like
The
like a B class star or something.
the surface temperatures can be as high as 210,000 degrees Kelvin. Okay. Good question.
Hey, Doug, this is Gus. I'm wondering if those nebula that you had on there, since they're so spectacular, that they may be Caldwell objects also?
I don't know.
Because I know I think the highest number we can go is 85 from where we are. So, and that goes up to 110 Caldwell, I think 109, 110. I would imagine if they're that spectacular that Caldwell may have added them to his catalog. Just guessing.
I don't know. They weren't, when I looked them up, they didn't say they were Caldwell objects. Usually it does.
The globular cluster NGC 4833 is a Caldwell object.
Okay.
It is Caldwell 105. And the other globular, actually both globular clusters in Musca are on Caldwell's catalog as 104, sorry, as 105 and 108.
Ah, okay.
Wow, so Caldwell got around.
Yeah, so Gus, if you want to see them, you're going to have to go south.
Yeah.
The Caldwell catalog is a catalog that goes through both northern and southern hemispheres. It's kind of like the Messier's version for people who can get around.
So Gus, are you working on your Caldwell?
I already finished it. I got the award and everything. So I'm done.
You don't have to see them all. You only have to see how many of them?
It was 50, I believe.
Okay, so you didn't have to go south to see them.
No, I didn't. No, I didn't have to do all 109, 110. No.
Okay. I believe there was an award for doing that.
I think it's 50 if I remember correctly.
Right.
It wasn't.
I think it's
more than that, but in that range.
I think the Caldwell has several levels.
Yeah, well, I think just to get the award is you get the 50 or 60, 70, somewhere around there. I forget what it is.
If you want to get them all, you have to go to the southern hemisphere.
Yeah.
Yeah, I want an excuse to go down there.
Oh, there you go. Go down there, Kay, and spend some time in Australia and pick up your Southern Hemisphere Astronomical League awards, like the Southern Sky Constellation Hunter.
Yeah, and I used to live down there. Dang, I spent 3 years down there. Could have done all of that.
Okay.
Can everyone see my screen? Moving on to our next and last topic for the night.
I can.
Yep, got it.
So I wish there are a couple more things I wanted to add to this presentation, but I ran out of time because school. Again, please, I need volunteers for presentations for April and May. Very much appreciated. But there, within the last 2 years, there have been a couple of really cool objects that have been found in the Milky Way that are on a pretty large scale. And so it was kind of an opportunity to go and dig around. It's like, what other things are, of these giant structures can we find in the Milky Way that we as amateurs can't actually see or don't even realize that are there? So to that, we're going to talk about 3 of them. One of the ones I wanted to include were the arms of the Milky Way galaxy, but I did run out of time. They are the Radcliffe Wave, stellar streams, and the North Polar Spur. And give me 1 second here to. Sorry, I was getting an echo from someone else's mic, so I just had to mute some folks. So the Radcliffe Wave was actually found in January of last year. It was found by looking into data from the Gaia space satellite, which is managed by the European Space Agency. For those unfamiliar with Gaia, it is a satellite that is basically producing a highly detailed 3D map of over 1 billion stars in the Milky Way galaxy. Basically, it's a representative sample of many of the stars that has produced several phenomenal pictures that you may have seen in various magazines or in the news. It is a massive string of gravitationally connected nebula that stretches over 9,000 light years, and is actually found within the Orion arm. And the Orion arm is it's not one of the Milky Way's 4 main arms. It's actually a sub-arm that comes off of the Perseus arm in the Milky Way. The other arms being the Sagittarius arm, the Orion, the Perseus arm, the Sagittarius arm, and I'm blanking on the other 2. It actually the size is so big, it's actually about 40% of the mass of the Orion arm, that is the arm of the galaxy that contains the solar system. So this thing is actually really huge. And it's like, well, how do we miss this thing for 200 years of modern space telescopes and other advanced techniques? And the answer was because we actually, in order to even know it was there, we had to use 3D mapping techniques from the Gaia data set, because Gaia is being used. Gaia is really hard to speak when you're tired. The Gaia data is very precise. It allows us to gain distance measurements on top of location for stars in the sky, so we can actually build a very accurate 3D map. Without that, you can't actually see the structure of the Radcliffe Wave. So since almost everything that we've done in imaging astronomy over the last, 100 years has been primarily 2D, there was no way for us to actually even identify it. So this is kind of to give you an idea. So the yellow dot in this image is our sun, and these red dots are all portions of the nebula that fall in the Radcliffe Wave. Kind of a better idea. So here, that Perseus arm and Sagittarius. So here are 2 of the, kind of give you an idea of where we are. So the Perseus arm up here is one of the main arms, and here's the Sagittarius arm. The Orion arm is kind of hiding smack here in the middle. So it actually goes from about here to over here in the North American Nebula. So this thing is pretty darn huge. So some of the nebula that are actually part of this wave include the Orion molecular cloud complex, which includes basically all the nebula in Orion that we can actually see. Go look at Orion tonight. It's always a cool object, a cool constellation, and a cool space of the sky to go stare at with a telescope. It also includes the North American Nebula, which is currently setting now. So you can actually, if you looked up at the sky and just followed along in the Milky Way, you would be able to see this thing for most of the year, or you could see elements of it in your telescope for most of the year. It's that big. The sun is actually passing, because it's a wave, as you can see here back in this picture. It goes through, and it's actually coming up and out of the Milky Way disk by a considerable margin. I think it was about 500 light years above the main galactic disk. Nope, go back. And the sun is actually passing up through this oscillating wave of nebulas, and it about 13 million years, it'll go through it again. There's, from some of the stuff that was published with when this wave was announced, is there like sometimes you might get mass extinction events from passing too close to supernovas or whatever. And there wasn't actually any extinction events that have been associated to passing through the densest parts of the wave. So it's probably just going to be another harmless, you know, we won't be here to confirm it'll be harmless. I don't plan on being at another 13 million years anyway. But, you know, harmless overall to life on Earth. There's also some speculation that the Radcliffe wave and one of its mini nebulas are actually responsible for creating the sun. That's kind of a harder one to pin down, just as things move around our galaxy. They're not all moving at the same speed, so the sun actually is moving in and out throughout the rest of the galaxy, and some may progress into the southern arm. So we're not actually quite sure, and that one's going to be pretty hard to give a precise answer of, like, did the sun actually originate from a nebula within the Radcliffe wave? I would not expect to have an answer to that anytime soon. From there, we move on to stellar streams, and this one was kind of was actually really cool to go look at. It's kind of hard to pin down an exact definition, mostly because Wikipedia doesn't have a really good one that I was, you know, caught to. These are a collection of stars orbiting a galaxy, which is a very vague and unhelpful way to say it's a type of star cluster, but it's not necessarily. The members of stellar streams were typically part of a globular cluster that is being torn apart, or from a dwarf galaxy that has collided with the Milky Way in the past. So, you know, when we say that they're orbiting, they're not orbiting in the sense like you would have with an open cluster, where they're all tightly bound to like a ball or a very small area. These are basically just long whips of stars that are stretching out far greater than what you would normally expect within a star cluster. It makes it actually very difficult to actually tell when stars are part of a stellar stream. We have to look at what their overall motions are through the sky with other stars. They're similar. They're a type of stellar moving group, which they're just this general unhelpful categorization of loose stars that form this a similar. There are a bunch of stars that are loosely moving together. For example, of a moving group, if you actually look at the handle of the constellation Ursa Major, all of those stars are actually part of a moving group. They're all moving together. So they're not, from our perspective, they don't look like an open cluster at all, but the stars are all actually moving in the same direction as a group as they move through our galaxy. So kind of hard to give you a really good definition of that. Hopefully it makes sense of what they are. Some key differentiators, as you can kind of see from this picture, is that moving groups and the differences between a moving group and a stellar stream is that moving groups are typically objects that are originated from our own galaxy. Stellar streams typically don't. Again, there might be from a globular cluster from a galaxy that we have absorbed, or from a dwarf galaxy that have collided with. So they'll actually have different ratios of hydrogen, helium, and other elements in them compared to other stars that we might find. The scale of stellar streams is also pretty much a deciding factor. As the image on my right shows here, there are a couple stellar streams. The large one that's looping around our galaxy twice is part of the the Magellanic stellar stream, which is being pulled out of the Large Magellanic Cloud. They can stretch out, for hundreds of thousands of light years all around our galaxy, which makes them, their scale something that's kind of like, wow, how did this get here? How did we not see this? So the first stellar stream was identified by a man named Olin Egan in 1971. He first identified the Arcturus stream, which includes the star Arcturus and the constellation Avoidance, as well as about 50 other members. And these were first identified because they're actually moving up and down through, well, like they're orbiting. If you imagine the Milky Way as a plate, they're going up out of the plate and back down into the plate, rather than going all along the plate's edges. So they're actually going up and over the Milky Way as they're orbiting. So they're actually not part of the, they're not moving in the, they're moving perpendicular to the direction of the sun, which is what was one of the key ways that we found them. The next stellar stream we actually had to wait a good amount of time in order to find was the Sagittarius stream, which comes from the Sagittarius dwarf galaxy. And I'm going to talk about this one here in a little bit. This stream contains about 100 million solar masses of stuff. So really, really big. And it stretches about 1 million light years. So it's actually wraps around our galaxy a couple of times. It's not one whole flat band of stars that stretches for 1 million light years. It's going, as we kind of saw on this picture, it's going up and around and through several times. So this is kind of gives you an idea of where the Sagittarius dwarf galaxy is. And let me go find my laser pointer, because I know this might be hard to see for folks on a different screen. Where's my pen? Come on. Laser pointer. So right here where my laser pointer dot is, this is the Pipe Nebula and Sagittarius in general. So the Sagittarius dwarf galaxy is actually down below it right here. This is the dwarf galaxy that is actively being consumed by the Milky Way. We're in the process of merging with it. And if you've seen a lot of pictures of this region of space, you can't even tell it's there. You don't even see this entire galaxy that's just colliding with us. We'll see obvious ones like, the large and small Magellanic clouds over here, or Andromeda or M33 up here, but we don't. This whole entire dwarf galaxy is actually almost within the Milky Way itself, and we don't even know it's there. So something really cool. So the last stream that we're going to talk about is called the Monoceros ring. And elements of the Monoceros ring are actually visible tonight because being in Monoceros, it's part of the winter constellations, and you can actually see some of it tonight. So it is currently thought to originate from another galaxy that we are in the process of eating, called the Canis Major Dwarf Galaxy. But there's some arguments going on right now where some astronomers don't even think the Canis Major Dwarf Galaxy is a dwarf galaxy at all. So they're still trying to pan down exactly what the Canis Major Galaxy is. It's also, if you find the article on Wikipedia, it's called the Canis Major Overdensity, which doesn't, very unhelpful name. But basically, it's a region of space that's very dense in stars that you would not necessarily expect to be for where it is. This stellar, the Monoceros ring, is about 200,000 light years long, and it also wraps around our galaxy several times. One of the first elements of this was the globular cluster Messier 79. So we've actually, for a better part of about 300 years, actually seen an element in the night sky that was potentially part of another galaxy in our own and did not know about it. The globular cluster Messier 73 is also one that shares this distinction. Messier 53, excuse me, stringing that together, is also another globular cluster which shares an extragalactic origin. So next time you go look at those objects, you're not actually seeing something that was formed with the Milky Way. It actually came from an entirely different galaxy. Who knew? And the last but not least of our superstructures is the North Polar Spur. This was first spotted sometime in the 1950s by looking at radio telescope data. It doesn't glow very much in the visible or infrared spectrums at all. There was a lot of uncertainty for many years on what the scale of the structure was. And this goes back to the general problem for determining any distances in the night sky, in that everything kind of looks as two-dimensional to us. So there was a lot of years where we weren't certain if it was just something that was just really big but very close, or super, super big but very far away. So there were sometimes, for a period, it was thought that it was part of an ancient supernova remnant, or a very large nearby gas cloud that had been energized by maybe another supernova. There were some simulations done on the 1970s, which, if for doing any sort of computation in the 1970s like this is really impressive, considering they didn't really have computers back then that could, like they do today. That opened up the guess that it was part of something on a much larger feature within our galaxy. And this was kind of hinted, and it actually produced an observation. It said if you can find a matching half that goes through the south pole of our galaxy, then we know it's not a local feature. It's something much, much bigger. We didn't really get an answer to exactly what the North Polar Spur was until about 10 years ago, thanks to the Fermi telescope. So the thickest region of the spur extends well above the Pipe Nebula, which we had kind of remembered from a picture about 10 slides ago. The central bulge, or the main thick elements here, are about 20,000 light years in diameter from the galactic core. And the large outer diffuse structure spans about 45,000 light years in diameter from the galactic core, and it stretches above and below the galactic plane by almost 45,000 light years. So this thing is just huge. This is all the gas within this is extremely hot. Going at 3 to 4 million degrees. So this is like the surface of the interior of the sun temperatures, or around the temperatures you would find in the outer corona of the sun. Very hot gas. We don't even see it. It's also expanding at around 300 to 500 kilometers per second. So it's very fast moving. The current leading hypothesis of where this thing actually came from is it was a gas cloud that was devoured by the supermassive black hole Sagittarius A star about 20 million years ago. And when this happens, when a black hole eats something, it can't eat all of it. Some of it's going to fall in the black hole, and other parts of it are going to get accelerated along the black hole's magnetic poles and get sent out as jets. So if you're familiar with black holes at all, you might say, well, that kind of sounds like a quasar. About 20 million years ago, if you looked in the galactic core, you might have seen something that looked very similar to that, just lighting up huge swaths of the sky as, we just utterly, ate a gigantic cloud of gas. Where the gas cloud originated, if it was from a galaxy that we have since eaten or were colliding with at the time, is, we're probably not going to know yet. I mean, this is something very new, but hopefully we'll know in 100 years what exactly it was over time. So to kind of give you a better idea, so this feature here, so here we have the galactic plane here stretching through the center of the image, and we see this this greenish red bubble that's just extending up and around the galaxy here. And then we get this is the thickest part. This is what was originally found in radio telescope data. And then what confirmed that this was not something local to us. If you look down here at the bottom, we get this much fainter portion of a bubble, which goes, you know, got this thick cloud here that extends very faintly off down this way. And you kind of see this other leading edge of the expanding gas right down here if you stare hard enough and squint, and it wraps back around. So this is like just this humongous feature that we just can't see. And it's always one of those, like, it's really cool that it's there, but you don't even know it at all. So that wraps up for what I have for the main topic. Are there any questions about some of this? You feel free to ask, because I realize sometimes I don't say things correctly. So
Connor, these were all pretty recent discoveries.
yes, two of them
So-
were within the last 10 years.
So it's like, is it because of newer devices that we have to look at things, or?
So as two of them, the specifically some of the stellar streams and the Radcliffe wave are actually directly attributed to data from Gaia.
Mhm.
And because the Gaia data set is essentially a large scale I'm going to butcher this word, astrometry data set, which is basically here are positions of stars, which bakes, when you have over 1 billion stars that you can get, you know, here's my position, here's the direction I'm moving, and here's how far away I am, then you can start combing through all that to find some really interesting features, like the Radcliffe wave, for example. Because without, you know, plotting these things into 3D space, which we haven't been able to do before, because we didn't really have all three of those portions in the same data set. We didn't really have, here's my distance, here's my velocity. In fact, for a lot of stars in our galaxy, we didn't have velocity measurements at all. So we couldn't really say this star is moving in this direction. So the Gaia has been instrumental in a couple of these larger galactic features. The others are, you know, as I said, we were found by Fermi, which was an X-ray telescope. So our ability to image X-rays and other wavelengths has become an increasing portion of what we can see. As in general, though, examining the Milky Way itself is kind of hard, mostly because it's a lot of gas and dust. It makes it very opaque to light unless it's in the radio and infrared wavelengths. In fact, there's an actual name in the astronomy community, let me go to this picture, where they refer to the galactic disk here as the zone of avoidance. And that's just because you for any wavelength other than radio and infrared, you can't see anything through it. So so seeing galaxies on the opposite side of the galactic core, for example, we don't know it's there unless you are looking in radio or infrared. So it makes our own galaxy much harder to study than, you know, the Andromeda galaxy, which you can look up and we're seeing almost face on.
Oh, you talked about the stellar stream. It kind of relates to the Trojan asteroids that we have in our solar system around Jupiter and around the Earth. That'd be a
How
good
so?
analysis.
How so? I'm not actually familiar with some of the asteroid groups in our solar system, so if you can maybe talk a little bit more, maybe I can give a better answer than maybe.
Yeah, we've got that large group of Trojan asteroids, are particularly around Jupiter.
So from what I do know is that the Trojan, and I think there's another group of asteroids, and that's on the opposite side of Jupiter. They're basically a group of asteroids that are caught up in one of the Lagrange points of Jupiter itself. So Jupiter is kind of pulling or tugging them along as it orbits. So it's not, I wouldn't try to draw a comparison between the two, because not even, well, obviously one of them is about stars, the other one is, you know, asteroid rocks, but the mechanisms for which they're moving are very different. One well, obviously they're both being moved because of gravity, but one is they're, being the parts of a much more massive object that's just been shredded apart by our own galaxy. The other is just stuff that has been collected up in Jupiter's, orbit over, the 4.5 billion years of our.
Hey, Connor,
Yes.
so you explained the theory behind where this the last structure, the big bubbles, came from.
Mm-hmm.
And you also gave an explanation for the stellar streams, the remnants of galactic collisions and us sucking up other galaxies and leaving stuff behind in the trail. But what do we have for an explanation or a theory of what caused the Radcliffe wave? Because like you said, it deviates from the plane of the galaxy by.
No, the Radcliffe wave is basically, it's not deviating through the galaxy. It's, so if you took
You said bumps above
let-
the plane of the galaxy.
let me get a second. So if you took a flat sheet of paper and you started to put your hands on either side of the sheet of paper while it's on a piece of table, and you started to push inwards, it's going to start compressing. So it's the whole thing is still in our galaxy. It's just being compressed like a wave, like the cresting of a wave that's
Yeah,
going up and out. So it's not like the other objects where they're completely outside of the plane.
Do we have a theory for what's causing that?
Not yet.
Okay.
Again, because this was only found, formally announced. The Radcliffe was only formally identified last year. So there wasn't any good thing. There's not enough data yet to kind of give an idea of how it actually formed.
Okay. That's fine.
Could,
I was just curious.
my guess is that if you've seen, you have other nebulas like the Orion molecular complex and North American Nebula, which all look like visually distinct nebulas in space. It's either that they're all actually they're not distinct nebulas at all. They're just part of a larger gas cloud, and that's, just faintly gravitationally bound together. So it would be essentially part of a molecular cloud that formed with the Milky Way.
No, I got that part. I'm not speculating in any way that they're not part of the Milky Way. I was just wondering what caused the wave structure to bump out of the plane.
Okay. I misunderstood your question. Yeah. That hasn't been determined yet.
Thank you.
It's still very interesting to see what will
That's a
happen.
perfectly okay answer. That we don't know. The only reason I asked, because you did give an explanation for the stellar streams and for the bubbles, the polar spur thing, and you didn't give an explanation for what's causing that Radcliffe wave. We don't know.
Yeah, the 14 articles I was reading about it actually never even went into what got into that at all. Is basically, here's this thing,
Okay.
here's what it's about. But
Got it. Thank you.
good questions.
Okay, there's a question in the chat from Peter.
I missed that. Let me go find my chat window. Where did it go?
Have stellar streams been observed around Andromeda?
I actually think there have been a few that were identified in Andromeda. I have to maybe double check there's an entire Wikipedia page that lists stellar streams that we know about, and I think there are a couple in there from the Andromeda galaxy as well.
And I think we've seen that same feature in many other places where there's been colliding galaxies.
Yeah,
we've seen the trails, what you'd call the stellar streams. I think we've actually seen that a lot around other galaxies that have had collisions.
So there with that, and that there would be a very common feature I would expect of a lot of large major galaxies.
Yeah, and I think we've seen it before. Have we seen the polar spurs around other galaxies? Bubbles.
potentially around quasars, active galaxies that have started to quiet down is where you would potentially see some of them. I don't have any exact examples off the top of my head, but those would be likely places you would expect to see these.
Okay,
If the hypothesis is correct in that the giant bubble is from a gas cloud that's been eaten by our supermassive black hole, then I would expect similar objects to appear in those types of situations where
Sure,
you
got
have a active galaxy.
okay.
Cool. Any other questions? Awesome. I'm going to end the recording. And I can go find all my buttons.